Now, this is the last lecture of compact linear operator. We already proved in the previous lecture if T is a compact linear operator from n to n dash, n to n, where n is a norm space, then it's a nullity of T lambda. So, nullity of T lambda, not a nullity of T, nullity or null space of T lambda, that is a finite dimensional. So that is the one result. And the second result of the range. So that we will prove in this lecture, the range of T lambda, which is a closed, if lambda is not equal to 0. So this is very important result and it is very tough result. So have patience to do this result. Now the given part is T from n to n, which is a compact linear operator. So first remind all the things that are in this theorem. So first is compact linear operator. So what is compact linear operator? If we have bounded set in n, that its image is relatively compact. So that is the first definition. Second definition, the image of bounded sequence has a convergent subsequence. It means if we have bounded sequence in n, then its image has a convergent subsequence. So that is the definition of a compact linear operator, right? After that, our purpose is when lambda is not equal to 0, then range of T lambda. So what is T lambda? T lambda is equal to T minus lambda I. So range of T lambda is a closed set. Clear? So next our result in this theorem is closed set. So what is closed? Closed means if we have limit point, then that limit point belongs to that set. It means it is a closed. Or we can say that the closure of any set is equal to itself. Then that set is a closed. Clear? So these are the definition of closed set. So we will prove this result step by step. Now first T is compact linear operator from n to n dash. So we already discussed the definition of compact linear operator, right? So we go through the result. Now range of T lambda, right? Range of T lambda means image of every value of n. So that is T lambda x, right? And T lambda x is also written as T lambda n because it is a range of T lambda, right? What is T lambda? T lambda is equal to T minus lambda I. Our purpose is to prove this range is closed. That is our purpose. So we will prove it with the help of contradiction. Suppose this range is not closed. Clear? So this is not a closed. It means its closure and this set are not equal. It means there is some point in the closure that does not belongs to this range. Clear? So that is because this is not a closed. It means this and this set are not equal. So this is a subset of this set, but this set is not equal to this set. It means it has some vector, some point belongs to this set, which it does not belongs to this set. Clear? So mathematically, there exists some P point belongs to this closure such that P does not belongs to range of T lambda, right? So that is mathematically. Now, if P belongs to range of closure, now as P belongs to closure of range of T lambda, then by definition of closure, there exists a sequence Pn in this RT lambda such that this Pn approaches to P. This is equation number 3. Now, what is this Pn? this Pn belongs to range of T lambda, right? It means Pn is the image of T lambda. Then it means Pn can be written as T lambda Qn, where Qn belongs to n. Why? Because P1 is the image of Q1, P2 is the image of Q2, so Pn is the image of Qn under T lambda. This is by definition. And Pn belongs to R of T lambda, Qn belongs to n. Now this Pn approaches to P. Then what is Pn? Pn is equal to this value. It means this term approaches to P. Clear? If this term is approaches to P, what is Qn? Qn is the sequence in N. It means this is some sequence. This is the image of some sequence which is a convergent. So remember this thing. It is the image under T lambda of some sequence which is a convergent. Yeah, we can say that this sequence, the image of this sequence is convergent, right? So if it is convergent, then it has a convergent subsequence also. So just remember the image of this sequence is a convergent, that is in equation number 4, right? Now this is range of T lambda, which is vector space. We know that, and every vector space contained a additive identity. So 0 belongs to range of T lambda. It means it is a non-empty. If it is a non-empty, also P is some element which does not belongs to range of T lambda. P is some element which does not belongs to range of T lambda. And 0 belongs to this set. It means P and 0 cannot be equal, right? So it implies P is not equal to 0. This is why this is possible. This is possible because P does not belongs to this set and 0 belongs to this set. So it means P is not equal to 0, right? So this is equation number 5. Now, this sequence approaches to P and P is non-zero. It means it does not approaches to 0, right? So this sequence from this is convergent, but it is not convergent to 0, right? So it converges to some non-zero number. So it is not convergent to 0. It is not equal to 0, right? So what is the nullity of T lambda? Nullity of T lambda contains only those vector whose image under T lambda is 0. And this image, T lambda image, and this T lambda Qn not equal to 0. It means Qn does not belongs to nullity of null space of T lambda. So this is by definition. Now this vector does not belongs to this set. It means distance between this and this is positive because it does not belongs to this space. So distance cannot be equal to 0. Here distance cannot be 0. It must be a positive. So distance is either positive or equal to 0. So because the distance cannot be equal to 0, so it must be greater than 0. It must be positive. Now, by definition, let we take dn, which is a distance between Qn and this nullity, right? If this is a distance, then by definition, it is an infimum of norm of Qn minus x, where x belongs to nullity of T lambda, and it is positive. We prove that because this distance is because it is a sequence, not single vector. So again, it is a sequence, not single vector. D1 is a distance of Q1, D2 is a distance of Q2. So it is a sequence of a distance. So remember, it is a sequence of distance which is a positive. Now, by definition of a distance, by definition of here, it is a distance D. Now we have by definition, this is what is Yn by definition of distance, if there exists any sequence which is ym in nullity of Dn such that this Qn minus Ym belongs to Dn, right? So this, so remember, this X belongs to nullity of T lambda, right? So these are vector. These are not single vector. It is a vector. So see these vector in term of sequence. So in term of sequence, it is a Q1, Q2, Q3, and Qn, M, and Qm plus 1, and so on. It means this vector can be represented as ym or yn. Clear? So it is can be written in the form of ym, but in particular, it is also written in the form of yn. Clear? Now this sequence in this nullity which satisfy this condition, but in particular, this may be same. We can take it as yn. Clear? So this is, if we take yn, then it is a dn. This is a dn. Now this limit m approaches in infinity, this is equal to dn. If this is equal to dn, then it means this value approaches to dn. If it is n, then it is again approaches to dn, because m is approaches to infinity. Now, our purpose is this dn does not convergent. It is a converge to infinity. That is our claim. Okay, this is not convergent sequence. So our claim is it is an infinite sequence. Now suppose it is does not converge to infinity, yeah, it divergent. So equation, suppose, yeah, we can simply say that suppose this equation number 9 does not hold. It means dn converge to some finite number. If dn converge to some finite number, let this member qn minus yn, now we take here say yn, is treated as xn. Clear? So what is this? This term is xn, and this xn approaches to dn, right? Norm of xn approaches to dn. Clear? So this is a bound convergent sequence. If it is a convergent sequence, so it is a bounded sequence in n. Clear? If it is a bounded sequence in n, T is a compact linear operator. If T is a compact linear operator, then by definition of compact linear operator, its image has a convergent subsequence. So that is a, its image has convergent subsequence. Now, since T lambda can be written as T minus lambda I, where lambda is non-zero, this T is taking, this T lambda is taken in this side, and this is taken as this side. So we get this values because it is non-zero. So taking lambda inverse on both sides. So what we get this. This is identity operator. So identity operator is equal to these values, right? Now this sequence xn, which can be written as ixn, which can be written in this form. Now substitute the value of xn, which is qn minus yn. Now again substitute, again operating. First operate with the t, that is this. Now second operating with the t lambda. So this will become t lambda qn, this term. Second t lambda yn. This yn belongs to nullity of t lambda. It means its image under t lambda is 0. If 0, so here this term will be, second term will be 0 because of this. Then we get this values, right? So qn minus yn can be written in this form. Clear? Now from this t qn minus yn, this has convergent subsequence by equation number 10, right? So see that equation. This is xn mean that equation. it has convergent subsequence by this. Again, this sequence is convergent. If it is convergent, first see, is it convergent or not? So this is by equation number 4. So equation number 4, this is equation number 4, this is a convergent, right? So if it is a convergent, then it again has a convergent subsequence. Every convergent sequence has a convergent subsequence. This sequence has convergent subsequence. This sequence has convergent subsequence. The difference has convergent subsequence. And scalar multiplication has convergent subsequence. Then left hand side has convergent subsequence. Clear? So left hand side, this sequence has convergent subsequence. Suppose this subsequence converge to some member Z. That is written in equation number 12. Now this T lambda is compact and continuous because of T. Because T is compact and continuous. So it is again compact and continuous. So by using the continuity, if this sequence converges to this point, then its continuous image is converged to its image. So it means T lambda, this approaches to this T lambda, right? Now this Y and K we already discussed belongs to null space. So its image is 0. So this second part will be 0. So it means this term, this Qn, T lambda Qnk, it converges to T lambda Z. Also we know that this sequence converges to P. This converges to this, and this at this time converges to P. So by uniqueness of limit, these both are equal. So T lambda Qn equal to P. Then what do you mean by this? It means it is an image of Qn, or image of Qn means P belongs to range of T lambda, which is a contradiction because P does not belongs to range of T lambda. So here I repeat once again, if we see this is from this P does not belongs to range of T lambda, right? So here we prove if this P does not belongs to range of T lambda, so this is contradiction. Our supposition is wrong. It means if our supposition is wrong, then this sequence converges to infinity. Clear? So that is a part in the theorem that will be used in the theorem. Yeah. So this is a basically a separate part, but used in the result. Now, because it is infinite, so we take its reciprocal so that it approaches to 0. So put an approaches to this. Now, an approaches to 0, whereas where n approaches to infinity. Clear? Now we take Vn, which is equal to En Qn minus y. Why we take? Because our purpose is to find the norm of sequence equal to 1. So norm of sequence will be 1 if it is a sequence over its norm. So An is a sequence, this norm, and this is a sequence. So this by this, then its norm is equal to 1. Clear? So norm of Vn is 1. Also, Yn belongs to nullity of T lambda. So its image is 0. Clear? If its image is 0, so T lambda Vn, which is equal to, by using this result, so this is a T lambda Qn because this is a 0. So this is a convergent. Convergent means bounded. And this approaches to 0. One sequence is bounded. And second sequence approaches to 0. So this product approaches to 0. Clear? So T lambda Vn approaches to 0 as n approaches to infinity. Again, using the result of I, identity operator. So this Vn multiply by Vn on both sides. This Vn become lambda inverse Tvn minus lambda and Vn. So this approaches to 0. Remember. Clear? Now, this TVN, this TVN. So we are taking this TVN. Clear? This TVN, Vn is a bounded sequence in n because its norm is 1. Clear? T is a compact operator. Then by definition, its image has a convergent subsequence, right? Its image has convergent subsequence. Similarly, this is convergent, so it has convergent subsequence. This has convergent subsequence. This has convergent subsequence. So Vn has convergent subsequence. Suppose that subsequence is Vnk, and this Vnk converges to V. Suppose it converges to V. If Vnk converges to V, now from equation 18 and 20, this is 20 and this is 18. From this, it approaches to 0. It means it's a T lambda image approaches to 0. It's a T lambda image approaches to 0. So T lambda V equal to 0. It implies V belongs to nullity of T lambda, right? This is nullity of T lambda. Now, again, we use this values many times, right? Now, take un. Here it is a un. Un is equal to yn plus 1 by an into v. Clear? So this yn belongs to nullity of t. This v belongs to nullity of t. This is a scalar. So this is a subspace. The total un belongs to nullity of t lambda. Clear? By definition of a nullity of t, by definition of Tn, so because it is an infimum, so every number, every member is greater than equal to d lambda. This is for every un belongs to nullity of t lambda, right? Now, this un can be written in this form: qn minus yn minus 1 by an vn. So what is this? This is vn by an minus v by an greater than equal to dn. So taking 1 by an outside because it is a scalar number, it is a number. So this 1 by an, this 1 by an into this greater than equal to d, right? So this norm of vn minus v greater than equal to an into dn. An into dn, this product is greater than equal to dn. And this number is greater than 1 by 2. If it is greater than this values, and this an into dn is some distance between them, that is a positive values. It is, so this is a greater than 1 by 2. Some epsilon, we can use some positive number. If this is greater than 1 by 2n, which contradicts the result 20, which contradict the result 20. So what is the result 20? So this is a result 20 because it means this sequence, this difference approaches to 0. But here, this sequence approaches to, this is greater than 0. So remember, it's maybe use 1 by 2, we can simply use it is greater than 0. So this is positive, this is positive. So this positive number, this is greater than 0. If this is greater than 0, greater than 1 by 2, so it means an into dn, we can also check that values an into dn. So that this is a dn is the positive number. We know that, and similarly an into dn. So this is always greater than 1 by 2. If it is always greater than 1 by 2, then it which contradicts 20, which prove the result. So what we prove? We prove by contradiction, because we suppose that if the given result is not true, then by taking contradiction, by proving the, by using contradiction method, we prove the result. Now remember what we conclude from the previous two theorems. We conclude if T is a compact operator, then its nullity of T lambda is finite dimensional and range of T lambda is a closed, or this is for lambda not equal to 0 because lambda is not equal to 0 in that case. So this is a finite dimensional and this is a closed. So both the result is very important. So this is for this. And here we prove another result, 0 contained in NT0 equal to NT0, then contained in NT1, then NT square. So that is a sequence, right? Here again we find a sequence. Clear? Now that we will prove here. So that is in opposite order. This is equal to capital N, right? If this is equal to capital N, this is containing this is containing this, and so on. In case of nullity, here it was 0 and it was subset, not here it is a superset. So this is a bigger space, this is a next space, this is a next space, this is a next proper subspace, and so on. Where T lambda, we know that. Clear? So now from this, our purpose is only prove this result. Clear? If this is a T lambda n plus 1 is subset of T n lambda n, right? So it means T lambda, which is equal to T minus lambda I, which is T lambda n. This is now this. Now using binomial expansion. So we take just using binomial expansion. It is a x, it is a y. So it is x plus y raised to power n, x minus y raised to power n. So this is a combination MCN, or we may write it in this way. Also we used this. Clear? So in order, if someone do not know about this, then he can use NCK. So by using binomial expansion, simple. So this may be written in this form. Clear? So this is a first term taking outside. So this is a next term. Clear? Now this T lambda n, this T lambda n, which is equal to u minus mu I. So this is a T lambda n. This is a mu minus I. So we are taking this total operator is equal to u, right? And this is equal to mu, and here it is a I operator. Clear? So this represented in the form of capital U minus mu I, right? So this is in operator form. Operator form. This is same as the u mu as a T lambda. This is a u mu. Basically, this converted into again its form. Now this is u minus mu I. Clear? So this is u and this is a mu I. Clear? Now this u into mu I, if we take this is a T and this is a, if we take this is a S, suppose. So this is a T operator because it is compact operator. The remaining operator, suppose C S. So this can be written as T into S, where S is equal to summation nk T raised to power k minus 1 minus lambda raised to power n minus k. So this is a product Ts. Clear? Now, since T is a compact operator, C is a compact operator, and S is bounded because it is a bounded operator, then we already proved the ST is also compact and TS is also compact. So in that case, this TS is a compact operator. So U is a compact operator, right? If U is a compact operator, then T lambda n is again a compact operator because that is written in the form of U. Clear? So this is a compact operator. First prove that all the operators are compact. So first to prove the series, we prove all the operators are compact. So it is a sequence of compact linear operator. So that we prove in the first step. Second step is, if it is a compact operator, then we know that dimension of its nullity is less than infinity. Already we do that. If t is here there is no need to of this result. Just if u is a compact operator, then its nullity is a finite dimension. Nullity of u mu is a finite dimension. Clear? Use that. So this is no need of this line. So, but this nullity of if u is a compact operator, so this there is no need of this line. If u is compact operator, then u n mu nullity of u n mu is less than infinity. So this is equal to this value. So dimension of this is less than infinity, and range, not range. Here correct. So it is a some mistake, clerical mistake. You may say that it is a range. Range. So range of t n lambda is closed. If range of t lambda n is closed, right? So we get range is closed. Clear? Now this t lambda 0 n, which what is this? It is identity. Identity of n is equal to n. Our purpose is to prove this result. N minus 1 is contained in n. Right? It is a very simple. It is very simple. If we take some vector belongs to this, right? Suppose we take x. X belongs to this. So what is this? This is a t lambda n minus 1 of suppose it is we take y. Y belongs to this. So what is y? Y is t lambda n minus 1 into x. Clear? So it is also belongs to this set, right? If it is belongs to this, then this is automatically, trivially, it is a part of this set. If it is a part of this set, then it satisfies this condition. So again, it is because it is the last theorem of the chapter. So that's why it may be most important, right? So this is the basic. The previous two theorems are very important. Now this the entire compact linear operator. For further study for this function analysis, there are a lot of books in the market, but the best books, as per my knowledge, the functional analysis by Erwin Kreyszig, number one. Number two, function analysis by P.K. Jain, and there are many other books. So I think for more studies you can find many other books, but these are the basic books of function and analysis. For further studies, so go through that books. Now this is the end of compact linear operator.